Hi, I'm Mark Weitzman. Welcome back to Quantum Field Theory: A Student's Perspective. Today we're going to go through Lesson 2. I'll lift that out. Lesson 2 on Lorentz Invariance. This is a very short chapter in Srodnicki's book. It's probably about 3 pages. But it's very important, and I suggest that every serious student go through every equation in those 3 pages, verify them, and then do all the problems in Srodnicki's book. I think I'll make a video on 1 or 2 of the problems, but you should work them all out yourself. Nothing more is involved than index manipulation and just symbol pushing. It's really very easy, but you have to get used to the symbols. Now, I put in this lecture, I'm probably going to go a little beyond what Srodnicki did, not too much, but I just want to show you what else there is, at least as pertains to scalar fields. The reason why there isn't that much in this chapter on Srodnicki is that he doesn't do anything but scalar fields in the first third of the book. So he leaves for later things like spinors and gauge transformations and all kinds of other stuff with Lorentz representations. Whereas a lot of the other books, like Peskin and Schroeder, they do like spinors very early on in the book. I gave the stuff pertaining to scalars here. Srodnicki is chapter 2. Peskin and Schroeder have these pages in these sections. Coleman has a little bit in his early lectures. Ryder has a little bit, and then he has a very good discussion of the, I'll mention it, but we won't cover it today, on how you get what Wigner developed, which is called the little group approach to the representations. Then Ramon has something a little bit more advanced in his early sections. And the main reference is Weinberg, which Srodnicki cites. He has a very detailed chapter 2 where he goes through all of this, and 2.3 and 2.4 are very relevant to scalars. So there's a lot of books and material out there, and they all use slightly different notation. As mentioned last time, the metric is often different, but sometimes they just write their equations, and I'll give an example of this later in this lecture, where they write two equations which just look different between Weinberg and Srodnicki, but they're actually the exact same equation, as I'll show. So let's get started. Before I get started, as I mentioned, there's a lot of stuff I'm going to leave out on spinors and all that other stuff. So later in the course, we'll get into some good stuff. The Lorentz group is usually represented as SO3, 1. The idea is in 4 dimensions, it's like an orthogonal group, but it's got 3 of the metric elements are positive and 1 is negative. And but as we'll find out, this is a 6-parameter group. And it's actually homomorphic to another group called SL2, C, which is the covering group. And this is the same relationship like SO2, the rotation group in 3 dimensions, which has 3 parameters, is homomorphic to SU2. So there's a lot going on here. I won't cover it today, but you can see, take something like SL2, C. What does this mean? S always means special, it means the determinant is 1. L means linear, 2 means 2-dimensional, and C means complex numbers. So basically, it's just a matrix, alpha, beta, gamma, del. Now, how many parameters does a general SL2C common matrix has? Well, each of these is a complex number, so it's 4 times 2 is equal to 8. But we have a condition that the determinant, alpha, delta, minus beta, gamma equals 1. That's what the special means. So this is going to be like, it's one equation. You might think it's 1 parameter, but these are complex numbers. So these are 2 parameters, 2 conditions. So it's 8 minus 2 equals 6 parameters. So that gives you a hint that there might be something going on between these 2 groups. And so I just wanted to mention that there's a lot of neat stuff with double coverings and topology and all that stuff, but none of that is necessary for scalars. So we're not going to cover any of that today. When you first learn special relativity, there's like an elementary level to it. You know, it's one of the easiest theories in physics. But so the beginning level, you know, is just these very simple equations, you know. T prime equal T minus Vx over the square root of 1 minus V squared. Remember, I'm always using C equal 1. X prime equal X minus Vt over the square root of 1 minus V squared. Y prime equal Y. And Z prime equals Z. And that's it. So really it's just like two equations, these two just go along for the ride. And with these two equations you can do a lot, you know, and in your special relativity studies you'll have, you know, analyzed Lorentz contractions, time dilation, you know, all kinds of nice effects, you know, E equal mc squared and everything. You rewrite Newton's laws in relativistic form and everything. So I'm assuming you're all familiar with this, but you have to be familiar with a lot more than this. Because once you get to the quantum field theory level, now it's all about, you know, covariant notation, so you should be familiar with like indices being upstairs contravariant, downstairs covariant, the metric, how to raise and lower indices, how to write electromagnetism in covariant form and everything. I'll, as the need rides, I'll go over this, but we're sort of assuming you're at this level here, and today I'm just sort of reviewing some of the finer points or some of the things that you may have missed in an undergraduate education. So let me start by going through something that's confused a couple of students that I know, surprisingly. Sometimes you'll open up a textbook, like on particle physics, and you'll see equations like, I may have to switch colors, I'm running out of pens here. Let's see how. You might see these equations written as T prime equal T plus Vx over the square root 1 minus V squared. X prime equal X plus Vt over the square root 1 minus V squared. So, you know, sometimes students get confused. They don't know whether there's a minus sign or a plus sign and everything, and you should be able to figure it out. Obviously, they're inverses of each other. But the point I really want to make is that there's a distinction in physics between active and passive transformations. Now, in quantum mechanics, usually we do active. I'm not saying all the time, but most of the time. And in special relativity, I'll just say relativity, we do passive most of the time, not all the time. So like, the question is, what do you do when you're doing quantum field theory when you're doing both of these things, or particle physics when you're doing both of these things? Usually they tend to use active, but they don't talk about it that much. So I just want to discuss it. First I'll discuss it in terms of rotations because it's really easy to see. An active rotation, let's say you have, this is your coordinate system. Let's say you have a blob here, which represents a particle or something, an object. When you do an active transformation, what you're doing is you're actually rotating the object. You should do it without changing it, and I unfortunately can't draw, so it changed a little bit, but you can see that this is how we would represent a rotation. We keep the coordinate system the same, and we move the object, the lab, whatever it is that we're interested in transforming, we move the objects. A passive transformation, on the other hand, is the reverse. Let's call this X, Y. In a passive transformation, what we're going to do, we have the object over here. In a passive transformation, we're going to rotate the coordinate system in the opposite direction. So that this would now be X prime, and this would be Y prime. So it should be obvious to any physics student that the relation of the axes, like in this particular case, before the transformation, my object was mostly along the x-axis, a little above the y-axis, and now it's a little bit to the right of the y-axis, but it's mostly in the y direction. And now in this thing, my observer is going to be using these x prime, y prime axes. I didn't draw it that well. This should be closer to there, but you can see it's the same thing. Relative to the x prime, y prime coordinates, the object has the same relation. So the parameters let's say let's say theta under an active usually go to minus theta under a passive. So if you do something like a translation where you move your object this way, to describe it passively, you would move your coordinate system in the opposite direction, in the negative direction. All of this is very simple, but somehow it can confuse some people. So when you see, a particle physics book saying, let's boost the particle in the x direction, and it uses a transformation like, x new equals x old plus v t over the square root. What it's basically saying is you're actually taking this is like an active transformation. I'm not changing my coordinate system, but my particle is now, before it was at rest or it was moving with a certain velocity, and now it's moving with a larger velocity given by v, and it's moving that way. So a lot of times they use, when we talk about a boost in an active transformation, we literally mean we're boosting it, we're moving the system. Whereas in special relativity, we're really boosting the observer. When you boost the observer, the particle that was at rest now looks like it's moving in the negative direction. So you can see how the parameters are related. Anyway, it's a small point, but you shouldn't let it bother you. And I said, for the most part, most books, I think on QM and QFT and particle physics, use the active approach. But I'm not saying they'll never use a passive approach. They might, but most of the time they're using the active approach. Okay. So the final thing, I don't know if we talked about it last week, I just want to get it out of the way, the summation convention. It just means when we have a term in an equation like this, it's x0 plus x1 plus x2 plus x3. when you have the same index, one up and one down, and if you have more, if you have like two up and one down in the same index, 99.9% of the time you've made a mistake. So usually you'll have only one up index and one down index, and it just means to sum. In most QFT books, I don't want to say all because there's always people like Weinberg who go back and forth. And Weinberg goes from 1 to 4 to 0 to 3 to imaginary. He uses everything. So most books use Greek indices like alpha, comma, beta, Greek. They go from 0 to 3. So 1 is the x direction, 2 is the y direction, 3 is the z direction, 0 is the time direction. They'll use like I, J, K, Latin indices for just the spatial parts, 1, 2, 3. Like I said, some actually use 4 for the time directions. Some real old books will use imaginary metrics. You don't want to screw with those. And then finally, this applies just really to product terms. So something like AI plus BI, that's not equal to A0 plus B0 plus A1 plus B1, ... It only applies to products. And it applies to each term in a product. So if I have like X alpha, Y alpha plus W beta, Z beta, this is going to be X0, Y0, X1, Y1 plus X2, Y2, X3, Y3 plus W0, Z0, W1, Z1, and so on. And another thing which sometimes confuses novice students is it should be very obvious that X mu, Y mu is equal to X alpha, Y alpha, is equal to X nu, Y nu. You can change the names. These are called dummy indices. You can change the names of them, but you can't change them to an index you already have. So if you have something like X mu, Y alpha, Z alpha, you can't say, hey, I'll just change the alpha to the mu and get X mu, Y mu, Z mu. It has to be, this is what's called a free index. It's not summed over. You can't change the dummy index to a free index. Like I said, that's when you get these mistakes where you have, 2 up and 1 down. So don't do that. Okay. All right. That's notation there. Use this board here. So I want to spend about 5 minutes just reviewing symmetries in quantum mechanics. So in quantum mechanics, as you all know, we work in Hilbert spaces. Or at least we claim we do, because we always get these Dirac delta functions and everything which aren't in the Hilbert space. And then we expand to what we call rigid Hilbert spaces. Seems like a kludge to me. Some mathematicians should invent a space that really encompasses all of quantum mechanics, where we can use idealizations like particle with an exact momentum p, or a particle located at an exact position. Even if physically that's not realizable, it's nice to use those idealizations because they help in the calculations. That's just my personal opinion. So what we have in Hilbert space is we have rays and vectors. and these represent states. Actually, it's the rays that represent the states. But some of you might not have seen this terminology and just gone with the vectors, which is okay. The difference is that a state should be represented by a normalized vector, and the phase doesn't make a difference. So a ray sort of consists of the set of all normalized vectors, call it psi 1, comma psi 2, comma psi 3, such that the norm of the psi's is equal to 1, and each psi, like psi I, is equal to, some phase, e to the I theta, where theta is real, of psi j. So in other words, all the vectors that are proportional to each other and differ only by a phase represent the same state. And of course, you can't superimpose different phases. You'll get different states if you take like one state with one phase here and then another ray with it. So I'm just talking about one ray here. And but most of the time we work with vectors, and we keep this in mind, that vectors can differ by constant phases. And then we just have, so we have vectors and a norm. And, you're all familiar with this. Phi comma psi is equal to psi. I'm using Weinberg's scalar notation here instead of the Dirac notation. I'll change it. We have that. It's linear. The norm is linear. I did it again. So it's linear, it's anti-linear on the first argument. Satisfies the property that the norm is always positive definite, and psi equals 0 implies psi equals 0. Okay, so this is our usual quantum mechanics. And then we have observables, which are represented by Hermitian operator. I'm not going to go into the distinction between Hermitian and self-adjoint and all that stuff. Too technical. So we have like A dagger equal A. And this guarantees that the eigenvalues are real. So those are the things we actually measure. And our definitions are phi, at least for I'll talk about the time reversal later. Phi A dagger psi equal to A phi psi equal to psi A phi star. Okay. Now, if you're in a state R, the probability that, let's say you're in a state R and you're asking are you in the state R n, this is just given by the overlap. This is our usual Born rule. And then the probability, let's say R is a basis here, orthogonal. I'm leaving out some obvious things, but probability that R goes to Rn, if we sum over all n, this is equal to 1. So we got to be somewhere. Now, a symmetry transformation is a mapping where we map the rays. So one observer let's say observer O, he calculates a probability. Let's say R goes to Rn. And our other observer, after the symmetry transformation, he's going to calculate the probability that R prime goes to Rn prime. In other words, the symmetry transformation, T, maps like R to R prime. And this has to be equal. That's what a symmetry transformation means. Means that each observer can use his reference frame and use his vectors as long as it's a symmetry transformation. Not everything is a symmetry transformation in life. You know, we can't double the size of everything and say nothing has changed. If you try it, you'll see that when your buildings collapse. Way back in the 30s and the 40s, Wigner, who eventually won a Nobel Prize for his symmetry studies, especially with respect to nuclear physics, he established that any symmetry transformation of rays, like R to R prime, can be represented by a unitary operator or an anti-unitary operator. So a unitary operator this has the property that it preserves norms and it's linear. So for almost all the symmetry transformations that we're going to study, they're going to be represented by unitary operators. What this means is we take the symmetry transformation T, we map it to some unitary operator, like T might be rotations. And you know how to represent rotations, you know, x prime equal x cosine theta, you know, you represent them by matrices or whatever. And basically each rotation, each matrix will be mapped to the unitary operator. And the unitary operator is not the rotation. The unitary operator operates on states, state vectors. So, you know, the operators that represent rotations, you know, when you use that, like e to the I, you know, sigma, let's say I'll write it, sigma over h bar, e to the minus I, and then this might be the vector that you're rotating it around. I'm sure you've all seen these kind of things, and let's say a parameter alpha. So this is the operator, and you can evaluate it and everything, but it's not the same thing as the rotation matrix. Okay, but this is not the whole story. There's also anti-unitary and antilinear operators. And Weinberg discusses this pretty good in this chapter. For the most part, these only apply when there's time reversal. And if you studied quantum mechanics, if you had a good undergraduate quantum mechanics course or a graduate level quantum mechanics course, you'll have studied time translations, and you get certain theorems like Cramer's theorem and some other theorems. But here what we have is a little bit different. We have whoops. I keep writing commas here. Any comma is just the same thing as this is Weinberg's notation for scalar products instead of the Dirac notation. So u phi u psi is now equal to phi psi. You might say it's the same, but you have to take that complex conjugate. That's the difference. And it gets even worse because it's antilinear. So you're going to have u alpha phi plus beta psi is equal to alpha star u phi plus beta star u psi. Okay. And because this is antilinear, we have to define that a joint definition won't work. So for a linear operator, I showed that phi L dagger psi, or I defined it as L phi psi. That's L is linear. But for an antilinear operator, it's phi, I'll use A for antilinear, A dagger psi is equal to A phi psi star, which is equal to psi A phi. Either way, you're going to end up with something with U dagger equals U inverse. So this is what I find a little confusing, is that for both unitary and anti-unitary we have this, but this isn't enough. There are differences between unitary and anti-unitary operators, but to be honest, until we do time reversal, and it might be a while before we do that, the only place where we'll probably do time reversal is when we discuss the PCT theorem, which I'll get to in a second. So for the most part, we're going to be only worrying about the unitary case. Okay. Okay. The symmetry operators, these U's, they form a group. And we will, in this course, at some point in time, discuss groups and various things like that. For now, you just have to know that, form a group. So all you have to know is that, U1, U2 is equal to like U3. In other words, if we have two symmetry operators and we do them one after the other, we also get a symmetry operator. This is known as closure. We have to have an inverse, so U inverse is equal to the identity. It's equal to U inverse U. So whenever there's a U, there exists an inverse operator. So that's inverse. We have to have a associativity. U1, U2, U3 is equal to U1, U2, U3, associative. You might think everything in the world has got to be associative, but in fact there are, we get into things like octonions, which don't obey the associative rule. So, and there actually have found some uses in physics, and some people think that they'll be very important. You can Google online on octonions in physics. Okay. And so these are the closure, inverse, associative, and then there has to be an identity. I should have put that first, but there's always an element I. Identity element. It's unique, just like the inverse is unique. So these are the 4 rules for a group. Now, I'm going to talk one more thing. Again, this isn't too important, but it is like a technical thing. And it's in Weinberg's book. He discusses it. Weinberg's very good at not passing over small technical details which don't really matter to the average student. And see, Svyatnecki starts with the basic equation for representations. We say we have a representation of a symmetry if the following equation holds. UT2, UT1 is equal to U T2, T1. So this basically says that we can rotate a little bit. Let's say T is a rotation operator. Get the unitary operator associated to it, and then we can multiply it by the operator associated with a different rotation, and the multiplication of those two will be the same operator that combines if we just did the rotation and rotation. So most books start with this equation, but this is a little bit, it's assuming something, and then Weinberg shows that really what you should start with is this times a phase, e to the I phi n t2 comma t1. This is like as general as you can. The n will depend upon what state psi we're in, and then these are the transformations, and so theta is a function of like everything. And the idea here is simply that if we have, if we have a vector and we're doing a symmetry transformation on it, we have a lot of vectors that differ by phases. And then we multiply by another vector, we don't have to have the same phase for that other vector. So we could end up with a phase factor. And one way to think about this, for those who know about spinors, for instance, when you rotate a spinor by 2 pi, you think you get back to where you started, but actually there's a -1 factor. So that's an example of a phase factor. And these things are called projective representations. And Weinberg shows that if you make some assumptions about superposition and various other things, this can be replaced by just, that is, it only depends on the symmetry transformations, it doesn't depend on the state. But you have to make some assumptions on that. And for those who know, there are things like superselection rules. And central charges. And the central charges, for example, comes up when you do a representation of the Galilean group. And if you look in Ballantyne's book on quantum mechanics, he has a long, he works it out and shows where the central charge arises from. But Weinberg does claim, and he shows, that you can get rid of all these things. You can get rid of these projective factors and the central charges and everything if you expand the group. Thus, for example, you might think your symmetry group is SO3, but Weinberg would say maybe expand it to SU2. Then you won't have that problem. Or we have the Lorentz group, maybe expand it to SL2, C. So these are just details. I just wanted to get them out of the way, just to mention them for those of you who don't have access to Weinberg's book. As I said, Sugnicki starts he just starts from here. And for scalars, I think this is perfectly all right.